have to throw something on the first dice, it can be either 1, 2, 3, 4, or 5, or 6. And in each case, I'm left with the 2 other dice, and I have to throw exactly the rest. So if I threw a 1, I have to throw a 7 with the remaining 2 dice. If I threw a 2, I have to throw a 6, and so on. So the number of ways in which 3 dice can throw the sum of 8 can be obtained by summing these 6 values. And similarly, the value here can be obtained by summing these 6 values, and so on. This is exactly the same if you would do exactly the same thing with a coin instead of a dice. What you would get would be the Pascal's triangle. In this case, you are getting something pretty similar. Once again, the property will be that the largest number will be always in the middle, and in both directions the numbers will decrease. So one possible way of solving this task is to actually do this dynamic programming. Where is the catch? The catch is in the precision. The numbers in this table grow quite rapidly. If you take the normal Pascal's triangle, and so on, and if you sum the rows, then you will get 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on. This is because each of these numbers is the sum of the 2 ones in the previous row. So to get the entire row, you count each of these numbers twice, and that's it, basically. So the sum of each row is twice as large as before. The same holds here. Here the sum is 6. The sum here is 36, 6 to the 3rd, and so on. So we have, like, I don't know, 1,000 dice. Then the sum of these values is 6 to the 1,000. This is an amazingly large number. But the range of these numbers is only 1,000 to 6,000. With 1,000 dice, you cannot get a result different than somewhere in this range. The smallest results you can get is 1,000 exactly. The largest results you can get is 6,000 exactly. So there are 6 to the 1,000 ways how to throw the dice. And these ways are somehow divided among these few options. So for many of these options, the number of ways in which they can be thrown is very, very large. But on the other hand, the probability that you throw exactly 1,000 is almost 0. The probability that you will throw 1,001 is almost 0 as well. So the solutions that just use, for example, doubles to compute this table will get wrong answer due to precision errors, because they will not be able to distinguish among these two very small probabilities. So there are 2 possible ways how to solve this task correctly. One of them is to do this, but to use large arithmetics to actually compute the huge numbers. Or the other way, which probably most of you used, is to notice this pattern, that the most likely answer is the one in the middle, and then just print the numbers from the middle alternatingly. So for even n, we start with, for example, n equals 2. Then the most likely answer is the one in the middle. There is exactly one such answer, 7, and we then call on 6, 8, 5, 9, and so on. For odd n, the values in the middle, there will be 2 of those. So for example, for n equal 3, the most likely, for n equal 3, the range is from 3 to 18. The most likely answers are the ones in the middle, which should be 10 and 11, if I'm not mistaken. So these are the 2 values printed first. Then it's 9 and the 12 and 8 and 13 and so on. And the last 2 printed values will be the 3 and the 18. The only special case, and this was the reason for many, many wrong submissions, is a special case where n equals 1. In this case, all the values are equally likely, so the correct way to print them is not 3, 4, 2, 5, 1, 6, but in the correct numeric order. So this was a nice little catch hidden in this pretty simple problem. All right, any questions? Great. All right, the second problem in terms of difficulty was probably the problem about cells in Excel. The spreadsheet problem. In this case, what you had to do is basically the hard part of this problem is converting between a number of a column in a spreadsheet and the name of the column. Everything else was, I think, pretty easy. You just have, well, if you have a table to convert one number into two numbers, you just use division and remainder. So this is the hard part. The labels in strings look like this. Z, then there is AA, AB, AZ, BA, and so on. And this is converting this into numbers, into, say, 1, 2, 3, 26, 27, and so on. Sounds pretty easy. It's just counting in base 26, right? So this can be done really easily, and at least this is what you think before you start implementing it. This is actually one nasty bugger to get the plus minus ones right. And the best way what could be done here is to realize that the constraints are actually pretty low. So what you could do, you could actually generate all of these strings. Basically, all you needed were, I think, 3 nested cycles. So you can generate this into an array. At this moment, you have conversion in one direction for free. You can take a number as an index into the array. You can find a string and output it. And you can be completely sure you've got the plus minus ones right. And the other direction is equally easy. Just take all of these, throw them into a hash map or into a map. So in C++, feel free to use a map from a string to an int for the opposite direction. You take this string, you get this int. So basically, this task rewards coders who can look for such ways to implement the solution. And this is something I believe is pretty necessary in the World Finals as well. In the World Finals, there are plenty of problems where implementation matters. And if you can think of such ways to make your life easier and to be sure you will avoid plus minus ones mistakes, then this is something worth doing, especially in the World Finals where the time limits, for example, don't matter so much. So even if you use a map in a problem, you should probably be all right. The logarithmic factor shouldn't impact you as much. So, or even, well, if you are sure that the test data is small, then you can always do this. All right. Any questions about this task? Nope. Great. And then what was the next easy task? Fool, yes. One task that many of you had was the task, any fool can do this. Many of fools could do it. This was basically a simple version of the general parsing task. Well, what you were given in the problem statement, is a context-free grammar, a very simple context-free grammar. And what probably most of you did was some top-down parsing. So you will write a recursive function that will check, is this a set, by checking whether this is a left brace, this is a right brace, and the inside is a sequence. And to check whether this is a sequence, you once again do a recursive call and so on. Of course, in order not to run out of time, you have to use memoization. You have to avoid recomputing the same thing again and again. And this is basically what can be done for any context-free grammar. So what you have is a string. And what you are trying to do is you are trying to answer whether the string could be generated using the grammar given in the problem statement. So the sub-problems in this case are that you take a part of the string, a continuous substring, and for this substring you will ask the question, from which non-terminals of the grammar can this substring be generated? And using such sub-problems you can then build the answers to larger and larger strings and then get the answer, can this entire string be generated from the non-terminal set? So this is the bottom-up approach, the dynamic programming view, and the other view, which is essentially the same, is the top-down view. So we will have a function we will have two functions, is set and is sequence, or I think maybe it was is list in the problem statement. Each of them will get only two arguments, the start index and the end index for the substring. And it will return a bool whether it is a correct set or whether it is a correct list of items. This function is pretty simple. It will check this character to be a left brace, this character to be a right brace, and then we will call and return this sequence on the middle part. And the other function so right now we want to check whether this substring is a valid sequence of items, a valid list. So what we have to do, we have to split it into a first item, a comma, and the rest of the list. So we will go through the string, look for commas, and each time we find a comma, we have to verify whether this is an item that is a character or a set. This can be done using a simple check if it is just a character, or a recursive call to isSet if it is longer. And this must be again a sequence. So we will do two recursive calls, again with shorter substrings. So we have these two functions recursively calling each other to check whether something is a set. We have to check whether the inside is a sequence. To check whether something is a sequence, we sometimes need to check whether something is a set. And if we now add memoization, so for each combination start and end, we will only evaluate this function once. Then the time complexity will be polynomial. The number of subproblems, the number of calls for each of these functions is quadratic in the length of the string. So if this is n, there are n to the n squared substrings and squared subproblems if we have to solve each of them in the worst case. Each call to isSet is evaluated in constant time, and each call to isSequence is evaluated in linear time because we have to try all the commas as the splitting point. So the overall time complexity of this approach is n cubed, and this is for n equal to 200 fast enough. All right, questions, comments? All right, then next task, was the game theoretical task, lentil key. This was the game with candies. And I was pleasantly surprised how many people got this quickly. So it seems that you got quite a decent background in game theory. At least some of you do. So usually if you encounter a two-player game in problem statement, the usual way these games are formulated is that the last player wins. The player who has no moves left is the loser. So this is usually called normal play. And this is the better known half of the game theoretical universe. Well, and this part is better explained. There's the Sprague-Grundy theorem that is really very useful in evaluating many of the games. And this problem actually was showing a little bit from the other side, which is usually called misère play. And this is you take a normal game and you reverse the winning condition. So the player who cannot make any move is the one who wins. And such games are notoriously hard to analyze. In many cases, the solutions to misère variants of games are not known until today. They are open problems. In this case, which was the simple game of NIM, the solutions for the normal play and the misère play are actually pretty similar. So we will start with the normal version. So what we have are n heaps of tokens. For example, the game can be played with candies, matches, or anything. The heaps can have different sizes. And so we have 5 items here, 3 items here, and 2 more items here. And each of the moves consists of picking a heap and removing some number of tokens from the heap, at least one, but there are no other constraints. This is exactly the situation from the problem statement. The heaps are colors of the candies, and the number of tokens is the number of candies of the given color. So in order to make a move, you pick a color, and then you eat some of the candies. So in the normal play rules, if the last player wins, this is a very well-known game. The optimal strategy is known for more than 100 years. And the strategy is to take the heap sizes, 5 and 3 and the 2, and to encode them into base 2. So 5 is 101, 3 is 11, and 2 is 10. So you record the heap sizes in base 2, and you compute their bitwise XOR, exclusive OR. So in each column, you compute the parity of ones. Here it is a 0, here it is a 0, here it is a 1. And the statement about this game is that the position is winning if and only if this result is non-zero. Why is it so? In order to prove such a statement, we basically have to show two simple implications, or two simple facts. First of all, we have to show that if a player is in a losing position, then all of his moves lead into winning positions. So he has no other choice but to give us a winning position back. And the second thing to show, if we are in a winning position, we have a move, at least one such move, that will bring the other player into a losing position. So this is what we have to show now. So the easier part to show, if the XOR of the heap sizes is exactly 0, this is a losing position, I claim. And what we can note, that after any valid move, the exclusive OR of the heap sizes will change. This is because exactly one of these numbers will change. And if you change one of these numbers, it cannot, the XOR, for example, if there would be another heap like this, the XOR is 0. And now, if you change one of the heaps, you cannot obtain XOR 0 again because the original heap size is the only one where it is 0. I can compute it right now. Here it has to be a 1, here has to be a 0, and here has to be a 1. If you change it to anything else, the XOR will change. So this was the easier part, and the harder part is that imagine a situation, for example, like this. So you have 3 numbers, or as many as you want. The XOR is non-zero, and what you have to do is you have to show that there is a winning move. There is a way to change one of these numbers to make the XOR 0. Where's the catch? The catch is that you can only decrease these numbers. These numbers represent heap sizes, and the valid moves are only to remove something from a heap. You can't add anything. So you have to show that one of these numbers can be decreased and to make the XOR 0. So what we will do, we'll go from the left to the right. We will examine the columns one by one until we find one where their XOR is not 0. So here the parity is 0, here as well, and this is the column we wanted. Here there is an odd number of 1s. So we pick one of these, any one, for example this one, and we change it from a 1 to a 0. So right now, all of these columns are okay. And moreover, what we did, we changed the 1 to a 0. We decreased the number. And right now, I'm free to change the rest of the number any way I like. Because regardless of what I put here, the number still will decrease. The most significant change was from 1 to a 0. So right now, I just drop this and walk through the rest of the number and compute what I need here. So this would be the winning move, one of the 3 possible winning moves in this situation. So this bitwise exclusive OR, sometimes it's also called the mean sum of the numbers, is the way to solve the original version of this game. The easiest way to solve the misof version is to start working, for example, on paper, or to write a simple program that will try all possibilities and to actually find out the losing positions for this game. And pretty soon you will discover a very similar pattern. So first of all, where there are differences, the difference is where there are heaps of size 1 only. This is a quite boring subproblem because if you have heaps of size 1, then there is basically no choice left. Each move has to look as I pick a heap, and I take the only candy left. So the only thing that matters in this case is the parity of the number of heaps. So for example, if we have 4 heaps with 1 candy each, that I take a candy, you take a candy, I take a candy, you take a candy, and in this case you would be the loser. So for heaps of size 1 only, we can solve this game very easily. If the number is even, then the second player loses. If the number is odd, then the first player loses. This is exactly the opposite case as in the original NIM. And if there are no heaps of size 1, well, else. So imagine we still have at least 1 heap that has more than 1 candy. In this case, what we want to do is we actually want to play the original game of NIM. Because in the original game of NIM, there comes a situation when some player in his moves creates such a situation. So we are in a situation, for the last time, we are in the situation where there is a heap with more than one candy on it. The player will pick this heap and remove some of these candies. And right now what happens is that this player who made this move has a choice. Because if he removes all of the candies, he will get some number of heaps with size 1. But if he leaves the last candy from the heap he chose, he will get the other parity. So he is actually the winner. He is the one who chooses the correct parity for him to win. So in this miser game, he can actually, he is the same person will get to make this choice, and he will make the opposite choice in order to win. So to summarize, so these are exactly all of the winning positions in the miser play NIM. Either at least one heap is larger than 1, and the position is winning in the original game, so the exclusive OR of the heap sizes is non-zero, or there are only heaps of size 1, and their number is even. These are the winning positions. And the winning strategy is, while there is at least one heap larger than size 1, I am playing exactly the original game of NIM. And when I'm decreasing the last such heap, and it has to be me who decreases is because of the being in the winning position in the original game. When I'm decreasing it, I will do the move that will change the parity of heaps of size 1, and then I will win by default. So this was the small change that was necessary to do in addition to solving the original game of NIM. All right, did this make sense? Questions? Excellent. What did we have next? For example, cyclic. So in this problem, your goal was to design at least one permutation that has some special properties for each size. This is basically an ad hoc problem. You don't really have any named algorithm how to do such a thing. One approach, if you are really desperate and don't know anything to do, is just use next permutation to cycle through all small permutations and check all of them whether they are correct or not. Just print this to standard output and take a look at it. In the normal context, you can also have them printed, so you have it on paper. What you are trying to do, you are trying to spot a pattern. If you see some regular pattern, for example, if you take the lexicographically smallest such permutation of each size, you will very likely see some pattern. The only thing left then is to generalize this pattern and to hardwire it into code. So in this case, what can be done is like, well, what we are doing is we are designing a permutation that's cyclic. So we have to fill it in element by element, like to make sure that the permutation is cyclic, that I have to fill it like this, for example. So here are the indices 1, 2, 3, 4, 5. So if I place the number 2 here, then I have to place another number here, for example, a 5. Then I have to place a number here to make sure I won't break the cycle. I will have only one cycle, so one of the other numbers must go here. A 3, here's a 4, and here's a 1. So now I created a cyclic permutation. And this one actually anti-monotonous. So it goes 2 to 5 to 4 to 1 to 3, and stuff luck because it's not. So one possible pattern how this could be done. Well, I will show you one that I came up with, but there are plenty of others. So I started with placing a 2 here. And what I did then is I had even numbers on the way there, and then used odd numbers on the way back. So after the 2, I placed the 4 here, a 6 here, and the 8 here. Here goes a 7, a 5, a 3, and the 1, like this. So this is a cycle. From 1 we go to the 2, to the 4, to 6, to 8, to 7, to 5, to 3, to 1, and we are where we started. And this is anti-monotonous. It goes 2, 4. So here it increases, here it decreases, up and down, and up and down again, and up again. So this pattern works for any even n, and for the odd n, you just have to change the end a little bit, and it can also be done. So this was basically a problem for someone to sit with a pen and paper and try to work out some pattern that works. Another way to solve this problem, I believe, is you take the values, you divide them. Well, dividing the values into a lower half and the upper half does not work because you have to interleave them, and this will be very hard to maintain a cyclic permutation. The cycle will then be jumping like back and forth, and so it is easier to do it similar way to mine, that the values next to each other are close to each other in value. Okay. Questions? All right, a little bit of geometry. All right, so in this problem, if I recall it correctly, you were given a convex polygon, and out of all its possible triangulations, you had to pick the one that is shortest, all right? So how to do this? Once again, what we could do as a first attempt, we could write a solution that tries all possible triangulations. Basically, this is an overkill because we are doing unnecessary work, but this is surely a correct solution. The only thing left, well, the only thing left, always the only thing left, is to optimize it. The basic rule of writing efficient algorithms was invented by the organizer of the USECO, the United States Computing Olympiad, Rob Kolstad, who formalized it as follows. There are only 2 rules: don't do anything stupid and don't do anything twice. So in this problem, we will try not to do anything stupid. We will only be trying out some triangulations, and we will try not to look at any of them twice. So in the beginning, we have the polygon. We can now start cutting it somehow. And it's completely up to us how we will be doing the cutting. If we will be cutting the polygon in some systematic way, it can only help us, because if we were to start with such a cut, we are getting two large subproblems immediately. And this is completely unnecessary because anyway we have to cut this part and this part separately. So it is much easier to realize that in each triangulation we have to have at least one triangle that uses two of the sides. So we can pick such a triangle, we can cut it off. Right now we can try to cut off such a triangle and such triangle, for example. What we are left is some subpolygon. And this subpolygon uses some of the vertices of the original one, but not all of them. Does this lead to a working solution? Yes. Does this lead to a fast solution? No. Why is this? Because there are still too many ways how to select these vertices. There is too many subproblems. If we have n vertices in the original polygon, then there would still be 2 to the n subproblems because each of the vertices can be or can be not present in the current subproblem. So we need an even more systematic way. And the correct trick, and this is a trick that can actually be used in many other problems involving polygons, looks like follows. Imagine that this is a triangulation edge. This is a cut we made at some point before. And the rest of the subproblem will be a part of the boundary of the original polygon. So there's just this only one edge of the cut. So to represent this subproblem, the only thing we need are two integers, the integer I and the integer j, representing the number of this vertex and the number of this vertex in cyclic order. So this is I plus 1, I plus 2, and so on. So now comes the trick. What we can do in the triangulation of this polygon piece, there has to be one triangle that contains this edge. The only thing we don't know about this triangle is its third vertex. And the third vertex can be any one of these vertices. So these are the possibilities to try. For example, we can try this to be the third vertex. And what we get, if we fix the value of k, we get two cuts. We can compute their lengths easily. We get one triangle. This triangle is done. We don't have to focus on it anymore. And what we got are two new subproblems. And again, you can see there is only one cut edge and the part of the original boundary. And once again, one edge and the part of the original boundary. So what we got are actually two smaller subproblems. And the optimal way of doing this triangulation is simply picking the k for which the optimal solution of recursive call here plus recursive call here plus the two lengths is minimal. And we start this by a simple call where I equals 1 and j equals n. So this is one side of the original polygon and the rest of its boundary. Right. Does this make sense? To make this complete, time complexity estimate, if we had n vertices, then there are order of n squared subproblems because each subproblem is determined by its beginning and its end. And to solve one such subproblem, we have to try order of n possibilities. So once again, the time complexity is cubic in the number of vertices. Yes?
Don't we have to deal with the case in which the polygon isn't convex? Doesn't it generate some kind of problem?
Wasn't it promised that it is?
It should not be convex. It's not necessarily convex.
Mm-hmm.
The permitted is.
All right.
The example polygon wasn't convex.
Well, the approach still works, but well, the only thing that is that becomes more tricky is the implementation of checking whether you can actually use this triangle. You cannot assume that you can do these cuts, but you have to check whether these cuts don't intersect any of the edges. And you only check those possibilities that can actually be made.
Without checking the algorithm, you can do it in, I mean, it's difficult to do it in a cubic, to still do it cubic algorithm. You have now some hints to see how you can do those checkings to maintain the
boundary on n was just 50, huh? Yeah, so as the number of vertices was only up to 50, what we can do is actually, if we don't know that the polygon is convex, if we have to check whether we can make the cuts, it's basically better to have a worse time complexity, have, for example, time complexity n to the 4. This is still fast enough with 50 vertices. And to check whether you can make this cut, you simply take this as a line segment, take in turn each of the edges of the polygon as a line segment, and check for intersection. If you don't need to compute this intersection, if you just need to check whether two line segments intersect, this is very easily done using vector products. You can take this one segment as a vector AB, and you can now take these vectors AC, AD, and check whether they look, the AC and AD are in different half planes from AB. This will tell you whether the points C and D are in different half planes, and you do the same check the other way around, and if both checks tell you the truth, then these two segments intersect.
But
Yeah.
you still can process all the light segments to see if they are true, and you can get a still cubic path over this path.
Yes.
Isn't there a case in which a cut doesn't intersect any segment of the polygon, yet still the segment isn't inside the polygon?
Yes, there is.
If you draw a half donut.
Yeah. One more thing you need is the point in polygon test, because, well, this is the canonical example of a diagonal that cannot be used in the triangulation. This one doesn't intersect anything, but it is completely outside of the polygon. So you have to, one more thing is to take this point and check whether it is inside or not. So basically, the lesson is, as with every geometrical problem, that there are plenty of special cases, and you have to be really careful about them. The best thing to have is some tried geometry library. So if you are planning to go for ASIM World Finals or a similar level competition where you can have pre-written code with you, then geometrical libraries are one of the best investments of your time, because this is nasty code and it's hard to get right if you are writing it from scratch. So it is worth trying it out at home, trying to submit it at online judges and check whether it correctly solves everything. So stuff like checking whether two line segments intersect has to be pre-written, and you just copy it from paper and such contests. All right. So now let's go back to combinatorics. Even. So in this problem, we are given a subset of integers, those integers that contain each of the digits an even number of times. And we have to enumerate them. So we have to convert the number k into the kth such integer. So the smallest ones are 11, 22, up to 99. And then there is 1001, 1010, 1100, 1111, 1122, up to 1199. Then the next one is 1212, 1221, and so on. And as in all such combinatorial problems, the problem to generate the structure, the item with some given index can be reduced to counting the items. So what we need to do is we need to be able to compute how many numbers of which length are there. This is the first thing we need. Once we know this, we can know at least the length of the number we are looking for. And then we will be constructing this unknown number from the left to the right. So what will be the subproblems we will be asking? Imagine that we already know, for example, that we are looking for a number of length 8. And the first three numbers in it are 1, a 3, and a 1. So how many such numbers are there? The only thing we need to know is that we are looking for numbers that right here contain an odd number of 3's and an even number of anything else. Because here is a 3 and it doesn't have a period, so there has to be a 3 somewhere here. So this is not such a large number of subproblems if you consider it correctly, because what we have each subproblem can be described by the two items the remaining length. In the case of the example, it would be 5. And by parities of digits. In that case, that would be 0, 0, 0, 1, 0, 0, 0, 0, 0, and one more 0. So there is an odd number of 3's and an even number of anything else. So these are the subproblems we will be encountering, and their count is pretty small because the length, as given in the problem statement, will be up to 20 only. It will fit into a 64-bit integer. And the parities, there are just 2 to the 10, which is 1024 different combinations. So this is good enough. Actually, there is an even better solution because we don't care which values are odd, which are even, and we can compress this information even further. But this is, I will leave this as an exercise for you. So what we will do is we will denote LXY, the number of such strings where the length is X and the parities are encoded into bits of Y. And to compute this number, well, the starting condition is L, 0, and 0 is 1, and L, 0, anything else is 0. So the empty string contains an odd number of nothing, an even number of everything. So there is one such empty string, and the empty string doesn't have any other parities. And for any greater length, what we can do, we can try all possibilities for the first digit. In this case, we are treating them as strings, so we will not treat the digit 0 specially right now. So there are 10 possibilities what's here. there can be a 0, a 1, a 2, and so on. And each time we have to fill the rest using one of the other strings that have a length that is 1 shorter and the corresponding parity. So to write this down, for example, in C++, L xy gets initialized to 0, and for I equals 0, I less than equal 9, plus I, so like this, we take the number of strings that are 1 letter shorter and have the correct parities. So the digit I we used has to switch parity from here to here. And in this way, we will compute the correct value from the shorter ones. So once again, using memorization or dynamic programming, we can compute all of these values pretty quickly. And now using these values, we can, first of all, discover the length of the number we see, and then going step by step, we can construct these numbers. So for example, we already know that the number starts 135, and 5 other numbers are missing. So what we will be doing is we are looking, for example, for 17th out of these numbers. So we will ask, how many numbers that match this pattern are there? We can answer this by looking into this table. At the position, length is 4, and 1, 3, 5, and 0 are odd. Then we will ask, how many such numbers are there? Once again, we look in the table, length is 4, and 3 and the 5 are odd only, and so on. And each time we subtract this from the 17 until we get the correct digit. Right? So basically, there is nothing surprising in this task. From its nature, it had to be some type of a dynamic programming. The most important lesson, I believe, is that you don't create the sub-problems in the dynamic programming task by what the problem statement says you. So the problem statement would induce you into creating sub-problems. What is the number of strings of a given length that have all the digits even? This by itself is pretty useless. What you need to do is to examine the combinatorial structure. What happens if I change the object? What happens if I add a number, if I remove a number? And to describe the sub-problems of the dynamic programming using this information I discovered by playing around with the problem. So don't let the problem statement confuse you, and do your own work and decide your own sub-problems in such a way that they work. All right. Yes?
How do you treat the case of the leading zero?
For the case of the leading zero, you can, in order to compute how many numbers have length 2k, you can take the strings that start with a 1 and have length 2k minus 1, and so on until a 9. So this is in this way you will get the count of numbers that have the correct length, and then you can already proceed. And for the first digit, you will then only try 1 through 9. Another interesting thing, this was enough to solve the problem. Now, if you want to get an even better time complexity, what you can notice is that, for example, if there is a 7 here, the number of such strings will be exactly the same as if there is a 9 here, because this is just substitution. So we can, instead of having the 2 to the 10 possible states of which digits are odd, which are even, we only have to have states none even, 1 even, until 10 even, and that's all. But in this way, it's a bit easier to implement if you treat each digit separately. Okay, so which problems are we still missing? There's getaway. I'm sure that's the last one I will be talking about. Oh yes, rearranging the furniture. So, once again, furniture. On the first glance, this is clearly a permutation problem, right? We have objects in some order. We have to rearrange them into some other order. So this has to be a problem that somehow involves permutations. So let's start by analyzing some easier sub-problems, some easier cases, and let's see what's going on. So for the first example, we have 4 objects. Here is a box that's heavy. Here's a smaller box that's light, 20. This one has 70, and this has, say, 50. What we need to do is a cyclic shift. So this is a simple cycle. We have to shift all the objects one position to the right. Right now, the question is, what is the cheapest way to do so? First of all, let's ignore the weights. If you have a cycle and you want to break it into individual elements, if you want to place each element in its correct place, what's the smallest number of swaps you need? N minus 1, where n is its length. This is very, very simple but useful knowledge, because if you have a permutation and you decompose it into cycles, this gives you quite a lot of information about its structure. And right now, you can choose any 2 elements, and you can swap them in the permutation. If you swap 2 elements that lie on different cycles, this will have the result of joining the cycles together. If you swap any 2 elements that are on the same cycle, this will split the cycle into 2 new ones. This observation, if you haven't seen it before, do spend some time later and draw it on paper and verify that this is actually the case. This is actually what happens if I now, for example, if I have this cycle, 1, 4, 7, 3, this is the direction of the cycle, 5, 6, 2. This would look like this in the array. 1 points to 4, 4 points to 7, 7 points to 3, 3 points to 5, 5 points to 6, 6 points to 2, and 2 points to 1. If I now swap any 2 of these numbers in the array, I will get a new permutation with 2 cycles, exactly 2 cycles. This is a very important observation. For example, if you were given a problem, here's an array, sort it using the smallest number of swaps. The smallest number of swaps you have to use is determined by permutation cycles. You take the original order, you take the desired order. In order to get from here to there, you have to make a permutation. And this permutation can be split into cycles, and the number of cycles actually determines the number of swaps you have to do. Because in the end, when you have the sorted permutation, and if everything is in its place, you need to have n cycles. And in each swap, you can only increase the cycle number by 1. And it is actually always possible to do it in this number of swaps, to break the cycles in such a way that everything will end where it belongs to in the required number of swaps. So going back to our problem, we know that in this situation in the picture, we need at least 3 swaps. Another thing we know, we need to move each of the objects at least once. Right now, we already have enough information to show that one of the solutions is optimal, and it is this solution. Take the smallest object and swap it with the object that wants its place. So in this case, we would swap 20 and the 100. So the 100 is happy, and 20 got here. And the cost was 20 plus 100. We now swap the 20 and the 50. The 50 is now happy, and the 20 is traveling on. The cost was 20 plus 50. And we now swap these two. 20 gets here. The 70 gets here, and everything is happy. And the cost of the last swap was 20 plus 70. So what we did is we solved the problem. We used the smallest number of swaps. And furthermore, note what happened. 100 was only moved once. We only paid the cost once. 70 was only moved once. 50 was only moved once. And all the remaining cost is the smallest possible item. So this is clearly optimal. There cannot be any better solution if this is the entire input. So right now, we are halfway to solving the entire problem. At this moment, it is very easy to let this problem deceive you and to make a mistake. The mistake now is thinking, OK, I've done it. I decompose the given permutation into cycles, solve each cycle separately like this, find the smallest element around its circle. So the cost is sum of its elements plus n minus 1 times the smallest one. Nope, this is false. Why is this false? Imagine yourselves in a room with 4 huge bookcases, each of them of a weight 1,000. And once again, each of these bookcases wants a different place. What would you do? Well, normally, if you have no other place, then you have to do the construction from the previous situation. But outside of the room, there is a flower pot. And you can really easily use this one. Swap it with one of the bookcases, and in this way, you got a very cheap item in the room, basically free space. You can then use it to move 3 of the bookcases, and then return the last bookcase inside. So if we were to solve this cycle separately, the cost would be 6,000. Using the small object, we will be doing 1, 2, 3, 4, 5 times moving a bookcase, plus 5 times moving the small object. So it's just 5,000 and some smaller amount. So this is the second situation that can occur in this task. We can use an additional object from some other cycle to solve another cycle. And which object is this? Well, there is only one option. We want to use an object that is as cheap as possible. So this has to be the globally cheapest one. And this is the entire solution to the furniture problem. We take this permutation, we split it into cycles, and for each cycle we compare the 2 solutions. One of them is solving the cycle alone. The other one is take the globally cheapest item as a help and use it to solve the cycle. And this gives us the optimal solution. All right? And for the last problem of today's session, this was get away. Oh, we still have forest. All right. All right, forest. Well, basically this problem is what's not so difficult. What we have is a set of non-intersecting circles and what we have to do is to compute visibility. We have to find those circles that are visible from the center and then use some criterion to evaluate what to output. But basically, the task is about deciding which of the circles are partially visible and which are not. What we should do is, from this point, we can compute the tangent lines to each of the circles, like this. This is quite easy to do. This is a secondary school geometry because here there is a right angle. So if we take the point where we are standing, the center of the circle, we are here. The center of the circle is here. This is the circle. And we want to find the point of tangency. What we can tell is that if we take the talus circle, then this point has to be the intersection. So as there is the right angle, it has to lie on this circle. This is the center of this segment, and the intersection of this circle and the original one gives us actually both the points, one here, one here. So each of the circles can actually be thrown away and represented just by a single line segment. It is important to realize that this line segment does not pass through the center of the circle. So if you want to, in this problem, it is necessary to sort the circles by distance from the origin to process them correctly. It is not correct to sort the circles by their centers. There are actually test cases that break this solution. You have to sort these actual segments, for example, by the distance of their center from the circle. So what we have are these segments. And what we'll be doing is a planar sweep. So we'll compute the angles at which a circle starts and stops being visible. And we will have a set of indices to keep the set of circles that are currently intersected by the sweeping line. We will start by a line that points upwards. And for example, we can, in order to avoid processing the beginning especially, what we can do, we can simulate two full circles of this hand. It will be encountering the events. A circle stops being visible, a circle starts being visible, and so on. And at each moment, we keep the set of circles that are currently intersected by this half line, and the closest one in this set is the one that is actually visible during this interval. So in this way, we can construct the set of visible circles and then find the one of them that should be output. It's actually not that easy not that difficult to implement, I believe. Given a choice between forest and the minimax triangulation, this is the one I would be solving. All right, any questions about this one? So, and finally, get away. This is basically in Slovakia one of the problems we use when we want to avoid people complaining, oh, we had everything done and so much free time at the end. So this is, after years, already a legendary problem that is sometimes used for fun in contests. But it has actually been already solved. So the story is we are given a rectangle. We are given a set of points inside the rectangle. And what we are looking for is the point that is farthest away from all of these points. So if you, in an alternate story, in the problem statement, I believe it was lava, and you are escaping the lava that is growing from all of these places. So here is lava, there is some more lava, and as the circles grow, that somewhere here will be probably the safest point. Another story is you are tethering a goat, and you want the goat to have as much area to eat as possible, and here are some precious flowers you don't want her to eat. So either way, this problem boils down to a geometrical structure known as the Voronoi diagram. What we can do is we can split, given a set of points, we can split the entire plane, or in this case the rectangle, into areas like this. For each pair of points, we can construct their separated line. So the axis of symmetry of the segment, like this. Here it would be like this. And for these two, it will be like this. The axes have to intersect in the same place. So right now, we can divide the rectangle as follows. And these areas, defined in this way, are called Voronoi cells or Voronoi areas, Voronoi faces of the set. Basically, what we are doing, imagine these are the post offices in your city. You are dividing the city into regions, and for this region, anywhere here, this is always the closest post office. Anywhere here, this is the closest one. Anywhere here, this is the closest one. Yeah. And once you construct such a Voronoi diagram, then the answer, the point you are looking for, has to be one of these intersection points, basically. Because, well, imagine that you are somewhere here, and you are trying to make the circle as big as possible. So this is the closest point, so this is the one you will hit when you start making the circle. Well, it should look like this. When you start making it bigger and bigger. Right now, if you move the center away from this point towards the line, the circle will be allowed to grow more. So you are escaping farther. So you will get somewhere here. You will get a circle like this. And once again, by moving away from the center of this segment, you are allowing the circle to grow until you hit this point where there's nowhere to go. So if you are standing anywhere else, anywhere outside of a line, you can improve your position by moving to the line. If you are standing on a line, you can improve your position by moving in one of those two directions. So the optimal place has to be in one of the vertices or somewhere on the boundary. So the task is about constructing this Voronoi diagram. There is a very complicated textbook algorithm that can do this in n log n time. This is basically not implementable in the solution environment. It can be done in n squared or n squared log n time quite conveniently. One solution how to do so reasonably well is for each of the points you can construct one of the faces simply by half-plane intersection. For each of the other points, you take the half-plane that is closer here than here. You intersect these half-planes and you get one of the faces. So if you have pre-written half-plane intersection in n log n, then you can construct the entire diagram in n squared log n, and this is fast enough. Half-plane intersection in n log n is actually quite easily constructible because of the point-line duality. This is a little-known concept that if you have points can be represented by coordinates. Well, if we are in a plane, of course, x, y. If we have lines, the lines, except for vertical ones are special cases. We will ignore those for a while. Lines can be also represented using two integers each, well, two numbers. For example, you can have a line y equals ax minus b. So here's a number, here's a number. These two numbers represent lines. And what we can do is we can have such a correspondence that point on coordinates a, b will be turned into a line with this equation and vice versa. And this is called the point-line duality, and it has all sorts of nice properties. For example, if you had 3 points on a line, then after we make this dual transform, you will get 3 lines that pass through the same point, and vice versa. And if you had 3 points that were, and so on. This is basically best done if you find this in a geometry textbook and read up on it. One of the properties is that if you have a convex hull with points, what you get with lines is the envelope, so basically the half-plane intersection you need. So the half-plane intersection and the polygon convex hull can actually be computed using exactly the same code without changing at least a character. You just take the lines you want to intersect, you treat them as points, compute the as convex hull, and then look at it differently. So this is quite a nice thing to do. One textbook where this is written in a very nice and readable way was written by Dave Mount. So if you type his name into Google and add point-line duality lecture notes or something like this, then you can find some useful material. All right. I believe that's enough for today. Questions? If not, then thank you very much.